All right, howdy folks. In this video, we're going to talk about how issues of conjugation can affect issues of basicity and acidity of some common amine building blocks. This content might be introduced in the chapter on aromatic compounds and resonance and conjugation. It also could be some content that is withheld until you have a chapter on amines. And so please make sure that you're viewing these videos in the order that makes the most sense to you. And again, if you haven't figured it out, we do try to color code the videos. So there's a little explosion in the top corner tells you what kind of question it is. And the banner going across the top on the left tells you what kind of chapter it's intended to be or what kinds of functional groups the content is correlated with. And so please do take advantage of those resources. Here, what I'll encourage you to do is try to answer these two questions with a brief pause in the video. And so go ahead and click pause right now. Okay, hopefully you're coming back after having made a guess at these. And again, I'll remind people that it's really important to your own learning to actually pause these videos and spend some time working with the material. It should really help you with some deep understanding. And then maybe when I point out some more of the subtle things, you've already thought about them, and it helps reinforce the thoughts that you've had, or maybe it'll address some questions that you might have. In this video, each of the molecules I've chosen are important to society for some reason. And so this particular molecule is actually a chemotherapy drug. And by the looks of it, it's probably a kinase inhibitor. And so it has a couple of different nitrogens. It actually has 4 different nitrogen atoms, if you can believe that. So let me circle those here. We've got 1, 2, 3, 4. And it has 2 of them are NHs. So I'll just put a box around these. And here, the question has to do with which NH is the most acidic. And when it comes to issues of acidity or basicity or nucleophilicity, because remember the most basic groups tend to be the most nucleophilic groups, and obviously that's not 100% true, but roughly they're correlated. So hydroxide, for instance, is more basic and more nucleophilic than water. And acetate anion is a weaker base and a weaker nucleophile than something like carbonate anion or a phenoxide. And so there is a loose correlation between pKa and nucleophilicity. All right, and so what we can do is think about how basic or acidic each of these groups are. And from first principles, the more inductively electron withdrawing groups are around, those tend to pull electron density and they help stabilize the anion. But usually I try to tell my students to play the game, where are my electrons? And so you can imagine a game show, with the flashing lights, where are my electrons? And if you can answer the question, where are my electrons? Usually you'll get an idea of if it is an unstabilized anion, or if those electrons can be spread around and diffused, that tends to make the anion more stable. And as a consequence, it becomes a less basic or less nucleophilic group. And I mentioned acetate before, and so acetic acid, remember, is more acidic than water or methanol. Let me just write OR. And the reason for that, of course, that we're given is that there's resonance structures here to delocalize that O-. So anytime that you're spreading out that charge, generally you're going to make the group more stable of an anion, and the more stable the anion, the less basic and the less nucleophilic it tends to be. So the first thing I'm going to do when answering this question is I'm just going to draw part of the substructure of this molecule as the corresponding anion. And I'm going to ask myself then, what's the kind of pKa? Is there some other place that those electrons can go? And here, this N- doesn't have any groups to delocalize. And so if I had to estimate the pKa of this, I might put it somewhere closer to diisopropylamine, which we might recognize because this is a common base for aldol chemistry in the form of LDA. So LDA is lithium diisopropylamide, and often we have a pKa that we're given of about 38 for that. And so based on that, we might estimate that the pKa of this NH is about 38. And so, and that's quite basic. Pretty much the only things that we know that are more basic than that are carbanions, things like methyl lithium or butyl lithium or phenyl lithium. This other one, if we deprotonate it, it actually has a lot of places for that negative charge to go. So we could have a resonance structure where we delocalize this negative charge into this benzene ring. And we can keep moving that negative charge around that benzene ring. And I'll draw the resonance hybrid here in a moment. But it's actually connected to two different aromatic rings. And so we could take that same negative charge and delocalize it into this benzene ring instead. And that actually lets us park the charge on a second nitrogen atom, which is often a really great spot for it to go. Just like in the acetate, putting the negative charge on another electronegative atom is great. And so oxygen or nitrogen are terrific for that. There. And we can keep moving this negative charge around. So not only can we park it on one negative charge here, we can park it on not only can we park it on one nitrogen, we can actually park it on a second nitrogen as well. So that ends up being quite great. And so if you take all of this together, I'm just going to take a minute here to draw the full resonance hybrid. And all of the places where that partial minus can sit are definitely going to be on the nitrogen atoms. It should also be over on this carbon as well. And then we can also put it over here and on this carbon as well. And so what you should notice is every odd position should be able to have the negative charge. And so one thing I really like about resonance is it's always 1, 3, 5, 7. And so as long as you can keep your odd numbers straight and you can count, you should be able to draw a resonance hybrid very quickly. And so if I number this nitrogen as being 1, I can go 2, 3, 4, 5, 6, 7. And then going the other way, I can go 2, 3, 4, 5, 6, 7. And so that checks. All of the odd counts from wherever I started with that charge are all the places where the partial negative charge can end up. In any event, we can undoubtedly say that this NH is going to be the more acidic NH, and it's going to be the more acidic NH because it can delocalize that negative charge into not only the top benzene ring, but also the bottom heterocycle. And so it should have a much lower pKa. Cool. Moving on to the second one here. This is the opposite now. Instead of asking us which nitrogen is the most acidic, now we have to identify which is the most basic. And so we've got 3 different nitrogens here. Now, nitrogens in their protonated state tend to have a different pKa than they do in their anionic state. So up top here, the anionic pKa was 38, and so that's the neutral amine going to the anionic form. And remember, as pKa's are defined, they're always defined for the acid. And so let's put all of those here. We just have a regular NH3+. This can be in equilibrium then with the neutral NH2, and this then can be in equilibrium with the NH-. And of course, these would not be all in the same flask all at the same time, because the difference in pKa here would be so monstrous that really only 2 of these species would predominate at equilibrium. This pKa with the ammonium salt being the acid tends to be about 11 or 12. And then the pKa here we said was about 38. And so much, much higher. For the above problem, we were worried about this pKa, but for this problem, we're going to be worried about this one. And the reason is we're going to be starting at the neutral amine, and we're going to be going back towards the ammonium salt. Just like before, what we want to do is play our game, where are my electrons? Because while being able to diffuse those electrons around makes that nitrogen more acidic, the corollary there is something that's more acidic is less basic, and it's for the same reason. If those nitrogen lone pair are localized, they're looking to pick up an H whenever they can, but if they're diffused and they're kind of pointing all over the place, they're much less focused on picking up a hydrogen. And so the most focused, the most localized pair of electrons is going to be the most basic one when they're all on nitrogen. So let's just go ahead and draw out our lone pairs on these nitrogens. And this one is the one that is doesn't have any functional groups around it. It's alkyl, it's alkyl, and it's alkyl. And so we can imagine that the protonated version of this would have that pKa right around 12. All the other functional groups are going to be much more acidic when they're protonated. And the reason for that is up top here, this nitrogen just like above, is going to be able to delocalize its lone pair into that ring as a resonance structure. And it's going to lose some of the basicity because of that. And then, of course, we can move that charge around the ring if we'd like. And just like I showed you before, all the places where that negative charge should be are going to be 1, 3, and 5. And so that helps explain why this nitrogen is less basic. It's because it's lost some of its electron density into that ring. And in this particular case, having 2 chlorides on the ring, remember those are weak electron withdrawing groups from that benzene ring. And so that's even going to start to pull some of that electron density into the ring from the nitrogen even more than it normally would. Our other functional group to consider is going to be over here. And this is not any old amine. And we'll notice that it has the exact same problem as the first one that we talked about. And that is that there is an aromatic ring here. And so just like this one, that nitrogen lone pair can be delocalized into the ring and pulled away. But there's an extra spot for this lone pair to go, and it can go all the way up into this carbonyl oxygen in the amide functional group. And so if I had to rank these nitrogens as being the most basic one first, I would certainly say that this one is number 1. Then I would say that this one is number 2. And then this one would be the least basic at number 3. And not only is that nitrogen the least basic, it turns out the oxygen is really the basic part of that functional group, not the nitrogen at all. And it's because that N lone pair is delocalized into the carbonyl already. And so again, if you can play the game, where are my electrons? You can really get an idea for what are going to be the most acidic and most basic functional groups. And the same question is used to answer both of these. Which is the most acidic, which is the most basic? Both come back to the most basic is the most localized electron. And as they diffuse out, you make a more stable negative charge, and that ends up making the anion the most stable. And when you do that, it lowers the pKa of that NH group. Okay, so hopefully that was helpful. There's a surprise bonus here, and that is to circle any nitrogens that are considered basic in this molecule. And the reason I put this on here is because a lot of these nitrogens now are in a heterocycle, and this is actually one of the DNA base pairs, adenine. And so it's a very famous molecule, and it's one that's partially confusing because it has so many different kinds of nitrogens in it. So I thought it'd be a good opportunity to talk about which ones are the basic nitrogens. The first thing one wants to consider is just go ahead and draw in all of our lone pairs then on the adenine molecule and scaffold. And then we should just figure out, are those lone pairs localized and focused in a way that they could be basic, or are they diffused or distributed in the molecule? And in this particular case, this nitrogen's lone pair is actually going to be used in the aromatic system. So if we count them, we have 2 electrons, 4, 6 from our double bonds, 8 from the double bond over here. That means that this lone pair has to be 10 to get us up to the Huckel number. And so that N lone pair is going to be hybridized as a p orbital as part of the pi system spinning around. And so because that lone pair, again, if you go back to where are my electrons? It's delocalized in the pi system to account for aromaticity. And so if that's the case, it's not going to be a basic nitrogen. And so we can just X that one out, not going to be basic. The next one that a lot of people would think would be basic would be this one. And the reason for that is it looks on its surface to be an aniline with that N lone pair hanging out outside the ring. And what's deceiving about that is we're going to have to draw some resonance structures. And so I'm going to change my color here. And just like we had up above, going all the way up, oh, it's pretty messed up, but way up here, that's that same motif where that N lone pair can swing down into both of those nitrogens. And so if we take that resonance structure, now we've clearly shown that this is the more basic nitrogen. That's where the negative charge is. And we have an additional resonance structure. Make sure I have the appropriate resonance arrow there. And now we have moved that negative charge to the other nitrogen. And so both of these nitrogens, it turns out, are going to be quite basic. And so I'm just going to circle those in green up here as being basic ones. And the same thing, it turns out, is going to be true with this one. And so on heterocycles, a quick kind of cheat that I use, which is pretty helpful most of the time, is that when you have something like pyridine, where there is a carbon-nitrogen double bond next to whatever you have your lone pairs on, most of the time that one's going to be basic. On the flip side, if you have something like pyrrole, where this Nitrogen has a single bond on both sides. Usually that nitrogen lone pair is going to be spinning around the pi system, and it's going to be non-basic. And then one that is a confusing one is when you have an NH2 like aniline. Because on aniline, it is basic, but on something like aminopyridine, it is not basic. And so hopefully that helps out a little bit. If you've been enjoying these videos, if you've got comments for us, please leave those in the comment section to this video. Also, please don't forget to subscribe to our YouTube channel. That's one way to encourage us to make some more videos. Really, have the goal here to cover all of the Organic 1, Organic 2 curricula space. And as a reminder, again, these videos are color-coded. So the explosion up here tells you what kind of question it is, and the label up top tells you which kind of chapter it should be. So please go ahead and use that. Subscribe to the YouTube channel. If you want the PDFs of the notes, please go ahead and find us on Patreon. And also as a reminder, feel free to like us on Facebook or Twitter. Thanks.